Hello students. Today we will study about centripetal acceleration. For that we consider the circular motion of a particle in the plane. It is described by r of t is equal to r naught cos omega t I plus r naught sin omega t j, where r naught and omega are constant. Here in this equation x component is equal to r naught cos omega t and y component is equal to r naught sin omega t. So we get x square plus y square is equal to r naught square, which represents a circle with center origin and radius r naught. Now let us consider the derivatives of this r of t. So first derivative, r dash of t is equal to r naught into derivative of cos omega t is negative omega sin omega t. So negative omega r naught sin omega t into vector I plus r naught into derivative of sin omega t is omega cos omega t. So plus omega r naught cos omega t j. Again we differentiate. So we get r double dash of t is equal to minus omega square r naught into cos omega t I minus omega square r naught into sin omega t j. Here minus omega square is a common factor. So taking it outside we get r dash of t is equal to minus omega square into r naught cos omega t I plus r naught sin omega t j, and this is r of t. So r dash of t is equal to minus omega square r of t, or we have the second derivative of r is equal to minus omega square into vector r. We know that the second derivative represents acceleration. So we have a of t is equal to minus omega square r of t. This means that the direction of acceleration is opposite to the direction of the position vector, because here we have a negative sign, and the magnitude of acceleration is omega square times the magnitude of r of t. Since the direction of acceleration is opposite to the direction of position vector r of t, we say that a of t is the centripetal acceleration. In this figure, at t is equal to t2, this is the position vector r of t2, and we know that v of t2 represents tangent at this vector. So this is the vector, this is the velocity vector v of t2, and at t is equal to t1, the position vector will be a vector from origin to this point, and this is the vector opposite to position vector, which is here the acceleration vector. Here a of t1 is drawn here, and v of t1 means the tangent vector at t is equal to t1. This is v of t1. Now if magnitude of velocity vector is equal to v and magnitude of acceleration vector is equal to a, then we can prove that a is equal to v square by r naught, because a is equal to, we have a is equal to norm of a of t, and we have a of t is equal to minus omega square r of t. So we have its magnitude, a is equal to omega square into magnitude of r of t. And what is magnitude of r of t? We have r of t is equal to r naught cos omega t I plus r naught sin omega t j. So its magnitude is equal to root of r naught square cos square omega t plus r naught square sin square omega t, that is equal to r naught. So we have a is equal to omega square into r naught. Now we have v is equal to norm of v of t. So v square is equal to norm of v of t the whole square, that is equal to, we have v of t is equal to r dash of t. So this is the vector v of t. So norm of this vector the whole square is equal to omega square r naught square sin square omega t plus omega square r naught square cos square omega t. So it is equal to omega square into r naught square. So v square is equal to omega square into r naught square. So it implies that v square by r naught will be equal to omega square into r naught, and that is equal to a. So we have v square by r naught is equal to a. Next we consider curvilinear motion in the plane. Many important applications of vector functions occur in regard to curvilinear motion in a plane, that is planetary and projectile motion take place in a plane. In analyzing the motion of a short range ballistic projectile, we begin with the acceleration of gravity written in vector form as a of t is equal to negative g vector j. If a projectile is launched with an initial velocity v naught bar is equal to v naught cos theta vector I plus v naught sin theta vector j from an initial height s naught bar is equal to s naught j, then we have v of t is equal to, we know that what is the relation between a of t and v of t? A of t is equal to d by dt of v of t. So we have v of t is equal to integral of a of t dt, that is equal to integral of a of t is equal to negative g j. So integral of negative g j dt, integrating we get negative g t j plus a constant vector c1. In this figure you can see that the projectile is launched from an initial height s naught j. This is vector s naught is equal to s naught j, and the initial velocity is v naught. This is the vector v naught, tangent vector at this point v naught bar, and it is equal to v naught cos theta I plus v naught sin theta j. So this is the x component and this is the y component. So this is v naught cos theta I and this vector is v naught sin theta j. Now here we got v of t as negative gtj plus c1, where c1 is a constant vector. We have to find the value of c1. For that we use the condition that the velocity at 0, the initial velocity is v naught, where v naught is v naught cos theta I plus v naught sin theta j. So we apply this condition, v of 0 is equal to v naught bar in this equation. So the LHS v of 0 and v of 0 is equal to v naught bar, and what is the RHS? RHS becomes 0j plus c1. So we have c1 is equal to v naught bar. So in this expression for v of t, we put c1 as equal to v naught bar, that is v naught cos theta I plus v naught sin theta j. Then we get v of t is equal to minus gtj plus c1, where c1 is equal to this vector. So v naught cos theta I plus v naught sin theta j. So it is equal to v naught cos theta into I plus negative gt plus v naught sin theta into j. So this is the velocity vector v of t. Next, to find the vector r of t, we know that d by dt of r of t is equal to v of t. So r of t is equal to integral v of t dt, that is equal to integral, we substitute for v of t. So substituting and integrating, we get r of t is equal to v naught t cos theta into vector I plus negative 1 by 2 gt square plus v naught t sin theta into vector j plus c naught, where c naught is a constant vector. Now we have to find this c naught. To find c naught, we use the condition that the initial height is s naught, that is r of 0 is equal to vector s naught, that is equal to s naught j. So put t is equal to 0 here, we get on the LHS r of 0 and r of 0 is equal to s naught bar, that is equal to RHS becomes, the first term becomes 0 and here 0, here also 0 plus c naught. So we get c naught is equal to vector s naught bar, that is equal to s naught j. Now back substitute for c naught, then we get r of t is equal to v naught cos theta into v naught cos theta into t I plus minus 1 by 2 gt square plus v naught sin theta into t plus s naught into j. So this is r of t. So the parametric equations for the trajectory of the projectile are x of t is equal to v naught cos theta into t, y of t is equal to negative 1 by 2 g into t square plus v naught sin theta into t plus s naught. We now consider an example. A projectile is launched from the ground level with an initial speed v naught equal to 768 feet per second at an angle of elevation theta is equal to 30 degree. Find the vector function and parametric equations of the projectile's trajectory. Find the maximum altitude attained. Find the range of the projectile. Also find the impact speed. Since the projectile is launched from the ground level, the initial height is s naught bar is equal to 0 and the initial velocity, that is v naught bar is equal to r dash of 0. It is equal to v naught cos theta into vector I plus v naught sin theta into vector j, where v naught is the initial speed and theta is equal to 30 degree. The initial speed is given to be 768 feet per second. So substituting, we get v naught bar is equal to 768 into cos 30. We know cos 30 is equal to root 3 by 2. So cancelling 2, we get 384 root 3 I plus sin 30 is equal to 1 by 2. So 768 by 2, that is 384 j. So this is our v naught bar. Now we know that acceleration a of t is equal to minus g into vector j, where we know the value of g as it is equal to 9.8 meter per second square, or it is approximately equal to 32 feet per second square. So a of t is equal to minus 32 j. So velocity vector v of t is equal to integral a of t dt, that is equal to integral of minus 32 j dt. Integrating, we get minus 32 t j plus a constant of integration, that is c1. Now to find the value of c1, we use the condition that the initial velocity is v naught, that is v bar of 0 is equal to v naught bar. So putting t is equal to 0 here, LHS becomes v naught bar, that is equal to, on the RHS this time is 0, so c1. So we get c1 is equal to v naught bar and v naught bar is equal to this. So substituting, we get v of t is equal to minus 32 t j plus this vector. So rearranging, we get 384 root 3 I plus minus 32 j plus 384 into j. This is the velocity vector. Now to find the vector r of t, we have to integrate this velocity vector. So r of t is equal to integral v of t dt, that is integral of this. Integrating, we get 384 root 3 t vector I plus minus 32 into t square by 2. So minus 16 t square plus 384 t into vector j plus a constant of integration c naught. Now to find this constant, we use the condition that r of 0 that is equal to s naught bar, and s naught bar is equal to 0 since the projectile is launched from the ground. So putting t is equal to 0 here, LHS r of 0 means 0, RHS becomes, here first time is 0 and this time also equal to 0, so only c naught. So we get c naught is equal to 0. So we have r of t is equal to 384 root 3 t vector I plus minus 16 t square plus 384 t into vector j. So this is our vector function. Now the parametric equations are x of t is equal to 384 root 3 into t and y of t is equal to minus 16 t square plus 384 t. Next, we have to find the maximum altitude attained, that is the maximum value of y of t. We have y of t is equal to minus 16 t square plus 384 t. So its maximum value is attained at a point for which the first derivative y dash of t is equal to 0. So y dash of t is equal to minus 32t plus 384 and it is equal to 0 implies that t is equal to 12 seconds. So at this time the projectile attains the maximum altitude. So the maximum height attained by the projectile is y of 12. We denote the maximum height by h. H is equal to y of 12, that is equal to, in this we put t is equal to 12. So minus 16 into 12 square plus 384 into 12. So we get h is equal to 2304 feet. Next we have to find the range of the projectile. So y of t is equal to 0 implies negative 16 t square plus 384 t is equal to 0. That is equal to negative 16 t into t minus 24 is equal to 0. And this implies t is equal to 0 and t is equal to 24. So the projectile hits the ground at the points at the times t is equal to 0 and t is equal to 24 seconds. And t is equal to 0 means the initial time. So the time that the projectile hits the ground after launching is t is equal to 24 seconds and the corresponding range is x of 24. We denote the range by r. So r is equal to x of 24, that is equal to 384 root 3 into 24. So it is approximately equal to 15,963 feet. Next, to find the impact speed which is given by norm of v of 24. So v of 24 is equal to, we put t is equal to 24 in the expression of v of t. So we get 384 root 3 I plus minus 32 into 24 into 384 j. So it is equal to 384 root 3 into I minus 384 j. So norm of v of 24 is equal to square root of 384 root 3 the whole square plus minus 384 square, that is equal to, here 384 is a constant, so 384 all square is a constant, so taking it outside we get 384 into square root of 3 plus 1. So we get 384 into 2, that is equal to 768 feet per second. So this is the impact speed. Now in this example, if we calculate the launch speed, that is launch speed means norm of v of 0, then it will be also equal to 768 feet per second. Now I conclude and thank you for watching.